very last talk that will be given by David Drabold, who is a distinguished professor at Ohio University. Dave obtained a PhD from Washington University and then was a postdoc at Notre Dame and the University of Illinois. He received many honors and prizes. The most curious of all of them I found was that he is a fellow of the Royal Numismatic Society. So yeah, I don't know what the story is behind that, but I'm sure it's an interesting one. David, very much looking forward to your talk. Are you unmuted, David?
Sorry. Yeah. Can everyone see the screen?
Yes.
Okay. So it's really a great privilege to be here. This fantastic collection of talks. And so I'm going to talk about something a bit different. We're going to get a little more theoretical again, but very much with an idea of trying to connect as much as possible to experiments, maybe in a different way. Get my pointer lit up too. Sorry. Okay, and so let me begin by acknowledging the people that made it happen. So these are graduate students of Christmas present, I would say. So this is Kashi Subedi and Rajendra Thapa, graduate student of Christmas past, Kiran Prasai. And I also want to acknowledge, for purposes of this talk, two senior collaborators, Michael Kozicki and Yago Velo at Arizona State. Michael and I've worked on and off for 20 years, and he had a key role in motivating the work that I'm reporting. So I'm going to sully his name by attaching it to this talk. I should also thank the US Department of Energy and the NSF for supporting the work. Okay, so let me just put you in the picture, as it were, about how people traditionally compute the electrical conductivity of a computer model of a material. It's obviously something that's useful to do because it's naturally a key observable. But I just want to make the obvious point. It doesn't tell us as much as we would like to know. It's just a number, of course, for the DC conductivity, or it's a function sigma of omega, say, for the AC case. So, and probably you have a limited range of omega that you're able to measure it on. So, and let me just continue with the description of how this is traditionally done. The tool to enable this calculation is something called the Thekubo formula. So this is celebrated work of Ryogo Kubo in the 50s, who was looking at the statistical mechanics of linear response and devised a many-body statement of extracting the conductivity in linear response. There are approximations to this, but it's a very sound, sensible place to start. For our purposes, what I would like to say is that we can view it as the mathematical tool that connects the stuff that we simulators and modelers compute, wave functions, energy eigenvalues, density matrices, stuff like that, to this key observable. A far more transparent derivation was devised by Mott in the 60s, and it's nicely discussed in the book of Mott and Davis, the famous book on electronic properties of non-crystalline materials. And it's nice to think of it from that point of view, where it's easy to see that the conduction arises from quantum transitions around the Fermi level. If you adopt a single particle approach, which is practically usually essential, if you can see my laser pointer down here, this is what you get. So this would be the alpha element of the conductivity tensor. So if you're interested in conduction along X, let alpha just be X. And the point is that you see the conductivity can be expressed in terms of fundamental constants. Omega is the volume of the cell. And the key bits are here. there's this sandwich of single particle states, psi n and psi I, with a momentum operator in the middle, squared. And then there's these are just Fermi-Dirac distributions evaluated at probably cone-sham eigenvalues. And so the structure of this emerges from the current correlation functions that Kubo used. And so this is a very convenient, actually surprisingly simple formula that tells you a lot about the conduction. Okay, but we want to generalize this. So in fact, I'll claim there's a wider world, and we would like to do more than just get our single number or our simple function. So in particular, what I would like to do is extract something about the conduction mechanisms. If you have a heterogeneous solid, a complicated heterogeneous solid, or perhaps an electronic device, it would be nice to know which parts of it are contributing to the conduction, how much, questions like that. I'm going to try to convince you that the method's really pretty simple. It's not hard to understand, and it's not really difficult to implement in any current density functional, or I suppose in principle, probably a Hartree-Fock code. We've implemented it with VASP. In fairness, of course, no work occurs in vacuum. I just want to mention a couple of very nice papers that are salient to this, although they're different. They're not directed toward devising practical schemes, although they're excellent work. There's a famous paper of Berenger and Stone. This really goes back to the heyday of the quantum Hall effect and so on, where there were expressions for the current density within a Landauer picture. And this was picked up by Oakeshott and McKinnon, who published a very nice study of transport paths or current densities for a particular random disordered system. Okay, so let me just indicate what's coming. In the next few slides, I apologize, but for the aficionados, I need to say a little bit about how I deconstruct the Kubo-Greenwood formula to obtain the spatial information. As I say, snoring's allowed, but please mute your microphone. And you'll see that the basic idea is simply to tear it apart and reassemble it in a specific format, which enables us to draw some conclusions about spatial character of transport. Okay, then we'll apply it to some, I hope, interesting examples. Right. Okay, so you saw the Kubo-Greenwood formula earlier. So I want to adopt G as a decluttering stratagem, just to put all of the stuff that's unessential into this G. And so just notice the form of this, which again, I emphasize is actually pretty simple. The guts of it really is this momentum matrix element. So Pij is a momentum matrix element between, say, two cone sham states. K is the block vector. Again, alpha is just a Cartesian index, x, y, z. P is the momentum operator. Clearly, the guts of this is this momentum matrix element squared. So it's pretty obvious that one can just write out the momentum matrix elements in this format here. And this motivates us, again, in the decluttering strategy, to define some objects I'm going to call Cij like this, that of course just are going to represent these two terms from these two three-dimensional integrals. Okay, and so this C is a somewhat interesting object. Again, it's well known, for example, from the work of Berenger and Stone and others. This is just the momentum operator applied to the jth cone sham state multiplied by the complex conjugate of the ith. Okay, and in particular, what I'm going to do is I'm going to define these on a grid in real space. So imagine that we have some fine grid in real space, call those points X. And so this is just some complex valued function that I have on that grid that's pretty straightforward to compute. Okay, so naturally, we can write the conductivity as a discrete spatial sum. That is to say, of course, we can just approximate the quadratures as sums. Let's do it. This isn't how we actually carry it out, but for simplicity, let's just suppose that we have a cube and we grid things up with the same spacing h in all three dimensions. Okay, if we do that, then clearly the conductivity can be written like this, and you can see where I'm going here, right? I'm trying to disentangle the spatial part of it. And this, again, we really haven't done much, but I would note that this is, of course, exact in the limit that h goes to 0. Okay, and so what the really salient bit, the part of this that's interesting and is going to lead us to some kind of spatial information about the conduction processes, we get that from this object I'm going to call gamma. Okay, so this is just, again, it's this sum over the G clutter and these complex valued functions. And notice the form of it. So it's an object times its complex conjugate at a different point. It actually looks a lot like the single particle density matrix. It's worse than that, but it has a lot of the same flavor. We've found this to be an interesting object. I would notice by inspection, it's Hermitian, it's also positive semi-definite. So I'm going to perhaps over-dignify it with its own name. I'm going to call it the conduction matrix because it has actually some quite interesting properties. Let me just point out, though, from the standpoint of trying to obtain a space-projected conductivity, that we have this property here, that again, the conductivity is just a sum, a double sum, not a trace, a double sum over x and x prime of gamma, like so. Again, this is exact as h goes to 0. So you know what I'm going to say. The natural spatial projection in this formulation is clearly to just sum out one of those spatial variables. So I'm going to call this object zeta the space projected conductivity. So this is a scalar field which conveys information about conduction activity in a material. It is, of course, by construction, a fact that if you do the double sum, you get a positive number, right? It's of course real. However, if you sum on only one index, you can get a complex result, hence the absolute value bonds here. Okay, so we will investigate this for some specific examples, but there's another theoretical aside I briefly want to allude to. If you think about, so we have a Hermitian matrix, we're physicists, right? Of course, we have to diagonalize it and think about it. And it's hard to interpret the eigenvectors of this as anything other than eigenmodes of conductivity. So if we diagonalize this in position representation, so we have eigenvalues, say lambda mu, and eigenvectors, these chi's, you'll notice that lambda has units of conductivity. And in particular, if we want to rewrite the conductivity in the spectral language of this gamma matrix, it just takes this form here. So you'll notice there's a sum on the eigenvalues, okay? But that's not it, because again, the thing wasn't a trace. There is this, I guess we'll call it off-diagonal correction as well. Notice, and this is actually quite useful, that we have the eigenvalues, the lambda mu's occurring in both of these spots. And I'm going to exploit that because it's going to turn out that gamma has a gigantic null space. So I don't really need that many eigenvalues. It turns out to be one of the most interesting features of this stuff. Okay, so we see, of course, the eigenvectors. If we take all the eigenvectors and put them together with this expression zeta s of x, this is exactly the same as zeta. We're just using the spectral representation. The interesting feature, however, is that in practice, we often require a very, very small fraction of the spectrum to obtain the full result. And I'll give you explicit examples, and I'll show you one counterexample at the end. But again, so this is in the language of the eigenvalues and the eigenfunctions of this matrix gamma. This is the space projected conductivity. And once again, notice the nice feature, sort of obviously, that the eigenvalue multiplies everything, right? So if we're interested in significant conduction activity, if we have 0 eigenvalue, that's the stuff that goes with it we don't care about. Okay. I was at a meeting a few years ago where I was chatting with Jim Phillips about this, and he actually said it in a way that I liked. He said this is sort of mapping the computation of the percolating paths onto a diagonalization. I think that's the right way to say it, and it's also built on ab initio quantities that are computed from, in this case, plane wave DFT. All right. For anyone who actually took my advice and took the nap, you can actually wake back up. That's the crash course in what we're doing. There's more we could say about that, and we can perhaps discuss it further in questions if you like. Let me just now talk about some examples. Volker kindly, I didn't know he was going to do it, but kindly gave a nice introduction to amorphous carbon. And indeed, it's an absolutely fascinating material, and it has an extraordinary degree of flexibility, and you got an excellent sense of that from Volker's talk. This is a low density phase of amorphous carbon, which will have all the sort of operative hybridizations. That is to say, you'll notice that we have red atoms, blue and green. The red atoms are sp3, and so those will be tetrahedral-like, something a little bit like what's out of diamond, probably with some disorder. The blue atoms are sp2, so this is more graphitic or more like graphene. So you have more 120-degree bond angles and a planar kind of bonding. And we also get, and it surprised me a bit, I must say, when we initially did this calculation, we get a fair number of these green SPs. So these are just carbon atoms bonded with two neighbors, right? So they form these chains. And so to cut to the chase, what do we have here? What I'm presenting is this zeta of X, this space projected conductivity. So I'm trying to show you where's the conduction action in real space for this system. And so this yellow haze here is a representation of that isosurface. And you can see clearly that there's a strong tendency to be on these SP structures, the green SP structures, although there are interconnections to SP2 structures. So that's what I'm trying to represent here to the right. This is just kind of a guide to the eye of the topology of the path, if you like. We run along this SP structure. Looks like there's a residual bit of an SP2, merrily hop along some more SP, run into a pentagon, and so on, in this kind of complicated dance of conduction through this material. I think some aspects of this are known. In fact, I remember I had a wonderful visit to Cambridge University with Stephen Elliott's group a few years ago, and Felix Mokanu, his student, actually pointed out that there were suspicions about this, but it comes out to be indeed his comment was right. This is a conduction pathway in this material. It would be it's interesting to imagine that if you wanted to design a carbon material with some interesting electronic properties, you can imagine that you might try to do things like build, gosh knows how you might do that, but build these SP structures or make sure you keep them away from the SP3. And if you want an insulating regime, of course, you'd want lots of SP3 around. How you engineer that, I'm not sure, but I suggest it would be interesting. And I should comment, this is a model we think is pretty realistic. It was made with VASP and a technique we called force enhanced atomic refinement, which is a way of making sure that it matches diffraction experiments too. And this was my student, Bishel Bauderai, who did this. This was in carbon a few years ago. Okay. So that's kind of the physical content. Now let me just make a sort of theoretical remark too. So I was telling you that I like this gamma matrix, and this sort of tells you why. Here's the exact, so in the middle here, this is the exact space projected conductivity. So this is this field zeta of X. if I compute this with only 100 eigenvectors out of actually 64,000, that turns out that's the dimension of the matrix we were using for this problem, 40 by 40 by 40. In fact, you can see they're completely indistinguishable. They're identical. In fact, even with 75 eigenvectors, it's almost perfect. And so again, this highlights the fact that a very large part of the spectrum of this matrix has eigenvalue 0. In other words, the matrix has a big null space, and there's really just a handful. Often there's just a handful of eigenvectors that you need. This can be understood if you look over here. This is the logarithmic plot of the density of states for the gamma matrix. It's not cone-sham eigenvalues or something now, it's the gamma matrix. And you see there's this huge peak at 0 as I advertised, and then you simply have really a handful of vectors that provide the whole answer. By the way, I'm giving you the red is the inverse participation ratio. So that's a simple measure of how localized the eigenvectors are. And you'll notice that there's a significant correlation between having delocalized eigenvectors and a substantial contribution to the conductivity, which is perhaps hardly surprising. Okay. Let me now try something a little bit different, really just to illustrate another kind of possibility. There's nothing at all that limits us to the DC case. That's what I just showed you for the carbon. But we could also look at finite frequency, in which case the question we're answering is more of the form, which atom is absorbing light at what wavelength, which again could be of interest in some applications. One could address this in lots of different ways. Because we're collaborating right now with Michael and Iago, we've been looking at amorphous silicon suboxides, which are really quite interesting materials, and in particular amorphous SiO3. Just to explain the material for a moment, if you haven't thought about this is a system. Let me put it like this. Let's start with SiO2, where everything is nicely bonded up. So if we imagine sort of sequentially, randomly depleting it of oxygen, so we have the theorist's tweezers, if only experimentalists had them too, where we can just sequentially remove these oxygen atoms and say, relax the network, eventually you'll get down to amorphous SiO3. SiO2, of course, is a superb insulator, but as you start creating these oxygen vacancies, you get a hopping conduction through the vacancy subnetwork. But the system is, of course, quite heterogeneous, and you can expect that if you tickle it with light of one frequency in one spot, it might behave differently than in another. And that's kind of what we were setting out to try to quantify for the first time. So in particular, for this system, if we shine light at two different wavelengths, we chose 2000 and 1600 nanometers, I don't remember why, we can see that indeed different parts of the material absorb light in those cases. And again, the underlying motivation for this, thanks again to Michael, is a potential application in computer security applications. And lots of nice physics in this system. Too much here for a short talk, and it's all rather complicated, but what we're illustrating up here with most of the colors of the rainbow, and actually some that aren't in the rainbow, are different kind of silicon environments after we've created these defects by losing the oxygens. And suffice it to say that, in fact, we do find that there's significantly different parts of the sort of defect subnetworks, if you like, absorb at the different wavelengths. Okay. This is really a bit of a one-off, and I'm not going to say much about it except to point out that it's a possible area of interest. Naturally, if you think about a liquid, there will be conduction fluctuations associated with the diffusive character of the liquid motion, of course. So we looked at every theorist's favorite liquid, which is, of course, liquid silicon. We don't do anything hard like water. of course, liquid silicon is a metal with a mean coordination of something like 6. And we just show here, and as I say, it's just food for thought, really. We show here how at some well-separated points in a simulation, it was at 2000 K, how the zeta function behaves as a function of time. There are technical questions one could and should ask about whether Born-Oppenheimer is valid here, and what, you know, an adiabatic approach is right. And I'm not sure. It's a starting place, but I point it out as something interesting, and I wonder if this could be probed in some experimental way. It's easy for us to compute some multi-point correlation functions if we can find an experiment to compare them to. Okay. I think it's naturally, it makes sense to apply this to some simple systems too, to gain some understanding and hopefully to build your confidence that it's sensible. So we thought it would be interesting to briefly present what happens with just FCC aluminum. To enable this, we built a 500 atom supercell, and of course, use periodic boundary conditions. We gridded up space on a 42 cubed grid to generate your favorite number, 74,088, as the dimension of this gamma matrix. We computed the space projected conductivity, zeta, both directly from the first form I gave you and in the spectral form. And it's really quite interesting to look at the structure of some of the eigenmodes. And I'll discuss one of those in a little bit of detail. Okay, naturally, we have to get a highly delocalized metallic kind of conduction, and we do. So that's what I'm showing you here to the left. It's highly metallic, and it's quite uniform. There are fine details to it that in fact are surprisingly sort of beguiling. So this is, if you look at the center of this and you blow it up and you egregiously change the colors, as I did over the weekend while wasting a few hours doing a little bit of art, you get structures like this. A colleague of mine saw this when we were discussing this, and she said, it looks like it's something psychedelic from Pink Floyd, which was indeed a brilliant insight, because without her knowing, I had named it Welcome to the Machine. And since I'm talking to a largely British audience, I assume you all like Pink Floyd, although I guess it's getting to be a bit old. Okay, so this passes a sanity check. By the way, of course, we're looking in real space, and these spheres naturally are aluminum atoms. You're just seeing the FCC lattice. Okay, so let's get a little more detailed about this. So here's the spectral density of states for gamma. And it's not quite the story that we had for carbon, where we had this almost negligible fraction of the spectrum required. Rather, here we actually need a few vectors, and maybe it's not surprising, right? We need a few vectors to really get it right. So again, here's the logarithmic density of states. And again, so this is conduction eigenvalue along here, and just the density of states here. And you can see, even for a metal, a very large number of eigenvalues are 0. They still are. Although, and this is different, there's a spectral tail that forms here that's between something like 0 and 1.2, roughly speaking. And I think it's not inappropriate to say that this is another mathematical or theoretical signature of the difference between metals and insulators. There's several of those known, and it's not that we desperately need another one, but I believe that that's a manifestation of this difference in this kind of spectrum. As I said, we need to actually get this right, we need a lot of eigenvectors. I'm really exaggerating. I don't think we need a third. But we need at least 10% or something like that, which is still what, 8,000 vectors or something like that. So again, this is a distinction with the sort of mixed semiconducting conducting case. There's a lot of degeneracy. So if you look here, you'll see that there are lots of cases of eigenvalues being degenerate with eigenvectors that look very similar. That's hardly surprising because of the symmetry of the FCC lattice, which is of course manifested in the cone-sham states, which is then somehow transmitted into these eigenfunctions of this gamma matrix. A curiosity, which I can speculate on, but I have no more answer than a speculation. The moment you'll notice that there's this curious spectral gap that seems to be forming at around 1.3 Siemens per centimeter. Whether that, I should comment, everything we're doing is at the k=0 point. It's at we're doing I don't want to use the word gamma, the k=0 point of the Brillouin zone. Okay, and it may well be. So this is a 500 atom cell. So it's not a silly approximation, but it also wouldn't shock me that if we integrated properly over the Brillouin zone, if maybe that gap would go away. We don't know, but I just thought it kind of curious to see that appear. The modes are actually quite interesting, and this is my favorite one, and I thank Kashi, my graduate student, for his artwork. And so this is just a heat map of one of these sort of 1.0 modes. And you can see that we have this structure. There are 4 of these objects, and then there's absolutely no activity with this white background. And once again, of course, the gray spheres are just aluminum atoms. And so this was a very interesting result. And again, these kinds of symmetries obviously are associated with the FCC lattice, but also the character of the matrix elements and everything else. And it turns out, and maybe this is a hint about what's going on, this is degenerate with other modes that are just rotations. And again, it's not like I'm claiming this is how the electrons move in aluminum, because we need thousands and thousands of these. This is just one, and it's pretty, so I wanted to show it to you. That's just the truth. Okay, and you'll see a little indication here of the color coding, which is sort of obvious: yellow, orange, red, black. Okay, and so I might point out that there are hidden structures here. So I want to just look at that mode a little more closely for a moment. There it is. So this is in the spirit of since I'm a fellow of the Royal Numismatic Society, I can tell you that this is a cross-pâté, right? Because I spend some time with medieval English coins, particularly. And what you'll see here is there's this sort of pencil of particularly high intensity, but then this very interesting, more diffuse structure around it. It obviously has some kind of a fourfold symmetry, and you see these kind of curious features on the perimeter. We can excise just one piece of this, and like all scientists, one wants to see the face of God in their work, except I'm a more modest man than that. So in fact, what I see is in my favorite dog's face. So this is Leo the Pomeranian, my son's dog. And actually, other than, it's true that Leo does not have the glowing yellow thing on his forehead. Otherwise, it's a pretty accurate representation of him. So this is a hidden symmetry that you probably didn't guess between conduction and aluminum and Pomeranians. Okay, let me be slightly less frivolous if I can for a concluding example. And this is a much more serious kind of example. Let me just quickly talk you through it. So I want to just mention something about, I guess I'll call electronic polymorphism in a conducting bridge random access memory material. Again, one of the pioneers of these materials is Michael, who got me interested in this stuff a long time ago. So such devices can be made in many different from many different compositions. One that's of interest is amorphous germanium triselenide, kind of strange stoichiometry, which you can then put substantial amounts of silver into. I mean, you can put 20, 30% silver in. Really interesting materials. They're fast ion conductors. And so you can actually manipulate the structure of the silver electrochemically, and you can make a very competitive, highly realistic memory device this way. And one could give many talks about this. I just want to give you a sense of it if you don't already know the story. So in trying to understand these things, it's natural to do traditional ab initio MD simulations at the given structure and density and see what you get, right? And if you do that, always the same thing happens. You get a model that looks good. It looks like pair correlation functions that experimentalists have measured, and it's always semiconducting with a typical cone sham gap of, I don't know, a volt or something like that. But it begs the question, so what's the conducting phase? So if you're going to make a memory device out of this, there's a conducting phase and a much less conducting or semi-conducting phase. And the genius of the device is that you can switch between these quickly and effectively. So how can we explain from a modeler's point of view how this goes? Okay, and like I say, if we just do the obvious thing and we just quench from the melt, we always get something that's a semiconductor. My former student, Kiran Prasai, is one of the main activities of his PhD thesis was working on something that we called gap sculpting. Okay, and the idea was, can we find a way to use ab initio techniques to engineer preferred electronic behavior? And that can take different forms. In this particular case, the idea was, could we take this semiconducting phase of this GeSe3 doped with silver and turn it somehow into the conducting phase? And the answer was yes. It's another talk about the techniques that Kiran devised for this gap sculpting, but we were able to produce another model. So this was the original insulating model you see here, and here's a metallic conducting model, and it's really quite plausible. Notice that the DFT energy difference between these is pretty small. It's only about 0.04 volts per atom, but there's a factor of 10 to the 8th between them in the two conductivities. The conducting phase has a conductivity of something like 100 per ohm centimeter. It's another story, and this was no talk is worth giving if you don't have your graduate students desperately mailing you something the night before the talk. So this is what we have, and we're confident of this. But what I can tell you is there's a conduction. The conduction is through connected sort of Ag2 Se linkages, and all this is, of course, in an amorphous environment. And part of the point is there's a general understandable view that when you have this conducting phase of these materials, it's because you just have some little nanowires of in this case, silver. And in fact, other work we've done suggests that's exactly right. If you look at copper in tantalum, or you look at copper or silver in other ionic systems like alumina. Okay, we published on both of those. The chalcogenides are a bit different, and here it appears that one does not have to have those fully wired together transition metal bits to get decent conduction. We could say more about that in questions if you're interested. Okay, I think I'm probably nearing the end of my time, so let me just draw some conclusions, and then I'll be happy to take any questions. So I hope I've convinced you that this is a practical scheme to obtain spatial information about charge transport. As you can see, it's readily implemented for any ab initio code, and you don't really need very much beyond what you already have, right? I mean, you have the cone sham states, you have the cone sham eigenvalues, and that's most of what you need. From a theoretical point of view, this matrix gamma is interesting because it often appears that its eigenvectors provide a highly compact description of transport in materials. And I hope I've have shed a little bit of light on a couple of examples. And I think I'll leave it there.
All right, thank you so much, Dave. That was really very cool and also very pedagogical. I felt like I could follow this derivation pretty much myself. Are there any questions for David?
Yeah, I have one.
Go ahead.
Yes, I was wondering if you'd looked at connecting your results to some of the analytical theories that people use to look at conduction and say oxides or disordered materials like hopping transport. Do you see evidence that the conduction is going through those vacancies or defects?
So this is an excellent question. I have not quantitatively connected it, but there's no question that the hopping is proceeding through the vacancies. I mean, the basic picture of those theories is clearly right. I mean, and so I'm not claiming that we discovered that, not at all. What I'm attempting to do is just be more quantitative about it by using, all of these fine details that we have available to us in the form of these wave functions and so on, that from these simulations.
And how do you deal with the role of temperature?
Okay, that's the best question of all. I wish I could have planted that question on you. That's a key question, and it's a bit of a scandal. And let me just publicly proclaim it. So if you do something like take any of these systems, even something simple like amorphous silicon, and you just do a thermal MD simulation at 300K. Well equilibrated, look at it after it's run for a long time, you find that localized eigenvalues associated with localized states fluctuate drastically around the gap. That is to say, the fancy way of saying that is the electron phonon coupling is large for localized states. This is something I've been pushing for years. And it is nothing that we took into account here, but if you wanted to really give a number for the conductivity, it would be absolutely essential to include that and include it well. We've done some of that elsewhere. Now, for purposes of this talk, I will tell you it's actually true that the kind of results I'm showing here are admittedly somewhat qualitative, but they're also pretty robust. But if you want to include the role of the temperature, you have to do it. The simplest way that I can imagine is you just do a Born-Oppenheimer simulation and you just average something like the Thekubo formula over a long constant temperature run. We've done that. That sort of works in amorphous silicon, doped amorphous silicon. But of course, one can imagine doing far fancier things with TDDFT and things like that. But this is a really an excellent question, and there's a lot underlying it.
Thank you.
All right, I think we're it's right at 5 o'clock. So this is basically the time we scheduled. So thanks again, David, and all the other speakers for really inspiring talks. And I think we put these disordered and amorphous materials into the spotlight today, and I think these materials really deserved it. Unfortunately, so usually we would continue discussions over drinks, beer, and wine, but this is unfortunately the sad part that's currently not possible. So thank you again, everyone, for attending, and in particular the speakers. Okay, take care. Bye-bye.
Bye. Bye, guys.
Bye-bye.
Thanks so much.